I'm going to be talking to you about simulation testing this afternoon. In order to talk about simulation testing, I need to do a little bit of classification of the various types of testing that we do. And I'm not going to say specifically unit testing or functional testing because those words have become kind of overloaded and a little difficult to define precisely. But I am going to classify things along these three axes. We have example-based tests versus property-based. We have white box versus black box. That's kind of a pair of terms that have been around for a long time. And automated versus manual. I find manual testing completely uninteresting, so we're not even going to talk about that. But I'll start by discussing example-based. What we call example-based testing is something where a programmer is writing code to exercise the system in some fashion. The programmer creates the test cases, the machine runs the test cases, and validates that the expected outcome is in fact the actual outcome. I have an example of example-based testing. It should look pretty familiar, but we'll use this as an anatomical example to dissect a test and see what the constituent parts are. So this particular test looks like sort of a table expressing some simple properties of addition. Because it's a pure function that we're testing, we don't really have any setup in this particular test. But in general, we'll see some kind of setup for a test. We have some inputs. These were chosen by hand by the programmer. Not a very imaginative set of inputs. I would say these are not the most interesting or perhaps taxing cases for testing addition. But nevertheless, we've got a set of inputs. We have the execution of the function in question. So we're doing plus over and over again. And we have our expected outputs. Those expected outputs are validated against the result of the execution by our phrase up there. And so these are kind of the parts that we expect to see in each of these tests. We have setup, inputs, execution, output capture, and validation. We see example-based testing in a number of places. We see it at different scales, where we talk about sort of the amount of the system that we're dealing with at once. This is where unit, functional, and acceptance testing gets a little blurry. You know, at what scale do you precisely change from doing unit testing to functional testing? I'll let other people continue to debate about that, as they surely will. We have different styles, sort of when in time are you writing your examples versus writing the code. And because we've been doing this for more than 10 years now, we've developed certain patterns and idioms, ways of dealing with creating examples, so that we visually see less of the framework and setup, and we see more of the inputs, execution, and output validation. This has been working quite well for some time. And I regard the development of unit testing as one of the biggest advances in software engineering that's happened during my career. I am not here to diss unit testing. Examples have their place. When you're exploring an unknown API, when you're trying to communicate to another human down the road that's reading your examples. These are all great uses of examples. But they do have some weaknesses when it comes to generating confidence that your system will behave as expected at runtime. And that's the kind of interest that I have in testing for today, is how do we gain that confidence that when we deploy our system, it's going to do what we expect. So examples fall down in a couple of places. First, the coverage is limited. Think about all the different numbers you could add, and 1 and 2 and -1 and -2 are surely the least interesting of them. I would say int max -1 is an interesting number to add. 0 is an interesting number to add. It's the additive identity. The largest float you can express plus the smallest float you can express. These are interesting cases. Our examples said nothing about those. Our examples also don't necessarily generalize. We certainly apply an inductive hypothesis and say if plus works for these dozen cases or so, it will probably work for every case we're interested in. But that kind of induction is not mathematically sound. And there are definitely situations in our programs where it doesn't hold that working for these cases means it works for all cases. So coverage is a problem. We've also found over time that having too many tests generates a lot of cost because the tests can become fragile. And it's particularly frustrating when the tests are fragile to things you're not interested in at that point in time. So if you've ever had to go back and change your setups for a whole bunch of tests because you trained mocks and now you've altered the actual behavior in a way that should be invisible to consumers, but you have to retrain your mocks. That's a kind of fragility that is pure cost without any benefit to offset it. I also think that unit tests don't scale particularly well. A larger and larger pile of unit tests takes longer to execute, but at some point you start to wonder, do I have as many bugs in my test code as I have in my production code? The answer is probably yes. You write 1 bug per 10 lines in every kind of code and every kind of language. There's also a slightly more abstract problem that's bitten me a number of times, which is that unit tests can verify the correctness of small pieces of code, say at the class level, but correct classes don't necessarily compose into correct systems. And so I can have A is correct and B is correct, but the combination of A plus B is incorrect. We've known for a long time that many bugs creep in at the interfaces between subsystems and between systems. And so I like simulation testing as a way to address these weaknesses. To get there, I need to talk just a brief bit about property-based testing, because simulation testing is a subset of property-based testing. So property-based testing says, instead of modeling specific cases of inputs and outputs, I'm going to model the domain and the invariants. And I'm going to state these again in code, but I'm going to let a program generate many, many input cases and individual tests, and verify the outputs against my invariants. The nice thing about this is that it validates properties of my system, not individual outcomes. And so if I'm doing my plus test in this fashion, I can validate that plus works for all pairs of integers. Well, no, we've heard today several times that all pairs of integers is going to take a long time to test. So in fact, we don't test all pairs of integers, but we test a large random sampling. And the more confidence we want, the larger the sampling that we test. And so we can let these tests run on and on, sort of as long as we're willing to wait for them. Some property-based testing frameworks also have a notion of famous inputs. So some famous integers might be 0, -1, int max, int min, and so on. Something that's common among many of these is that they will attempt to find a failing case, then minimize that failing case and present you with the minimal condition that reproduces the error. This is a very handy thing, and we see it in some libraries. I'm a Clojure dev, so the one that I like most right now is TestCheck. Very excellent library. TestCheck lets us express these properties in code like this. So we have a name of the property, which is useful for me when it fails. We have a quantifier for all. As far as I know, this is the only quantifier present in TestCheck, but it's usually the one you're most interested in. Then I have this binding form here that produces an input generator. This particular input generator is the int generator being passed through the vector combinator. So the combinator returns a new generator, which will generate arbitrary vectors of ints. And it will, in fact, generate the empty vector as well. So you can get some extra assurance that way. We then have the function under test, this sort. And I've just pulled it out for clarity in its own binding to S. And then I have a validation. Well, the property says sort preserves length. And so I'm asserting that the length of the vector before sort and the result of sorting the vector have the same length. Now I could also assert that the resulting vector S is in ascending order. Or I can split that out as a separate property. I personally tend to prefer splitting it out as a separate property so that each property names kind of one essential concept about the thing I'm testing. So this is property-based testing in a nutshell. I encourage everyone to use this no matter what. It's just a great practice. When we move on to the scale of whole systems is when we get to simulation testing. And if I go back and classify it on the original set of axes here, simulation testing would be regarded as property-based, white box automated testing. So the essential ideas here are to extend property-based testing from individual functions to whole systems. Again, we're going to have the programmer model the domain. Then we use a program to generate a script of inputs and actions. And this script is meant to be repeatable. So we actually try to contain all the non-determinism at the time of generating the script. We don't do randomness while executing. And we avoid randomness there because we want the execution to be as repeatable as possible. We are testing against the real system. So if you were here earlier for Will's talk, they were building a whole simulation of the system running in one process. In this case, we're running against a real running system. Obviously, that does introduce some non-determinism. And so part of the considerations we have to apply a little later on is how do we avoid that non-determinism from invalidating our results. And we also validate these properties at a global level. So with a unit test or a scripted functional test, we typically validate properties as we're executing the test. And we report failure immediately and abort that test run. This is good, but incomplete. By deferring the validation until after the fact and validating everything at the end, we can validate global properties, such as, did all of my API calls return OK? Did all of my pages respond within our response time SLA? Now, obviously, something where you're asking about all of them is something you can't do as you're executing. You have to defer that until the end. We can also ask about logical properties relevant to the domain. Did all the money in balance all the money out to the very last penny? Or did Richard Pryor creep in and start stealing fractional cents? Okay, 4 people got that joke. Sorry, a little dated. Now, before I go into the specifics of simulation testing and how the pieces go together, I just want to say a little bit about testing and the way that I regard it. We're not testing to prove our system right. That's actually a logical impossibility. We're testing to try and prove it wrong. So we're searching for failures. We heard this morning about searching the state space. I think we're actually searching trajectories through the state space that arrive at forbidden locations. So a forbidden zone of the state space may say, I've created inconsistent results in my database. And I want to find a sequence of actions that result in that forbidden outcome. So it is a search problem. And in the context of this search problem, I think code coverage is enormously misleading. It's a will-o'-the-wisp that we sometimes chase in an effort to gain confidence. But I don't think that knowing every line of code tells me much about the state space that my system can occupy. So we do need to limit our execution time, though, because if we try to fully explore the state space, well, Joe did the math. We need 2 to the something huge number of universes for a single machine, let alone multiple machines, let alone exploring different interleavings of operations on multiple machines. So we want to get the most we can out of the time, which means exercising many trajectories, but we will typically bound this on the amount of time we're willing to spend executing. Okay, after a number of gentle slides, I have to put this diagram in front of you. And I know your first reaction is, that's a lot of parts. It definitely looks like a lot of parts. All right, it is quite a few parts. But each part is there for a reason, and each part does only one thing. So let's talk about how these parts interact. These parts are decoupled via immutable databases. We tend to use Datomic for fairly obvious reasons. The idea is that each part can run repeatably. And so when we look at the generator up front, that's going to use some randomness to generate a script. Execution, system setup, capturing the outputs, validating the outputs, all of that should be completely repeatable. So as a reminder, the parts of the test we expect to see, and here's how they map into the diagram. So we begin with the activity model. The activity model is where I express, in a small number of parameters, how I think that the inputs to this system are going to behave. This will typically look like distributions, state transition models, and sort of bounds on inputs. The setup happens by initializing the target system. The size of this setup can vary from nothing at all, if your tests are fully independent of anything that's gone before. It can be a small amount of preloaded data, or in some cases can be a set of API calls to create a certain expected state in the target system. The execution runs purely off of the script. So we have a simulation runner, maybe more than one box, executing a number of processes against the system under test. And while this is going on, we capture the output. That output is going to take a couple of forms. We record what we're doing with the test itself. So we record that we had these actions and what sequence we ran them in. We also record the overt outputs of the system. And sometimes we instrument the system under test and record interior states of the system. This may take the form of additional APIs that you put into it so that you can call it from the execution and record the results. It may be as simple as just capturing the log file from the system after execution. So we store all of that in a database, and then we can apply validations in the box cleverly labeled validation. And those validations, some of them are true-false. So you either pass or you fail. Did everything come back with a 200 response code? Okay, you passed or you didn't. Other validations may be more qualitative. So how is the system performing? You may be able to map response time distributions into a red, green, yellow type of status. So it's not always the case that you're going to get back a straight thumbs up or thumbs down. And of course, you need to report this. So large amounts of data being produced, you'll definitely need some way of comprehending that data. If you don't boil it down to just a stoplight, you probably want some kind of charts or data viz. Now, we have released an open source tool called Simulant. Some of you may have heard of it or used it. Show of hands, anyone who's used it? Cool. All right, excellent. This is an example of simulation testing that we've put out there, and I'm going to walk through in a little more detail some of these pieces and show you what the code looks like if you're using Simulant. Simulant, by the way, works with Datomic, as you might guess from the URL, but it works with Starter Edition as well as Pro, so it is possible to get into this with $0 expended. So I mentioned the model, described it as a small number of parameters relative to the nature of your system. This is what one of the models looked like. This particular one is an expression of state transitions. So the model simply says a user interacting goes through these states. We have weights over there. They're normalized to whatever the sum of the weights for outbound transitions are, and a randomized delay of up to that amount. You'll notice a couple of variables here in these lines about these multi-session odds. That's a parameter that represents, for a given user, how likely they are to come back or to return to the site after they've interacted once before. So how likely are they to create a new session? And you can see that we're representing that as part of a transition probability that we normalize to 100. This is just a way of expressing a Markov model with some closure code. What we do then with the model is we sample the Markov model and generate event streams from one per member of our population. So this is how we sample it. We're using a library from Craig Andera called Causatum. Basically, you feed it with a model like that, and it gives you back a sequence of states and times. And whenever it reaches a terminal state, it stops. So I can call this repeatedly, and each time I get a lazy, finite sequence of states to visit. That's the entirety of the model for this particular system. Now, you can certainly make more sophisticated models. This one is basically just rolling uniform distributions on all of the variables. The parameters that I mentioned take the form of those weights and the multi-session odds. Multi-session odds is coming from a database where we can change it on each instance of the model. The others are kind of hardwired in code because, frankly, sitting there tweaking a bunch of Markov probabilities is a waste of time for a system like this that didn't have any existing traffic data. But you could certainly use existing traffic data to extract or train a model based on real user activity against a system or a site. We've had some simulation systems where we've used a naive Bayesian classifier to say what are the probabilities of transitioning to different states given the history that we've seen so far. So you can build a memory in. This particular system also only models one population. In this case, it's the population of users. But you can definitely create a model for multiple populations, say ordinary users and administrators, or buyers and sellers. We take the results of the model and we feed it into a generator. The purpose of the generator is to sort of unfold that model into an activity stream as large as we want. That activity stream is where we confine the randomness. So this is what the generator looks like. When we sample that activity stream from Causatum, we get back a sequence of state names. This is using a multi-method to dispatch on the name of the state we're transitioning into, and in each case generate a data structure. This is basically saying, give me a vector with the results of calling action. It's just a data structure. And then that becomes the action in the activity stream that represents that state transition. Again, we've kind of set up this model to be straightforward. One state transition typically becomes one action. Actually, we've got some that become no action. So entering the idle state, we don't need to do any interaction with the target system. This is what the driving code for that looks like. The first function up there, generate actions, basically says I'm looping over all the agents that I need, agent being a member of our population, and sampling the states for each one, generating actions on entry for each one, and then returning that as a list. You can see the action function here, just returning a map, merging in some keys from the specific action. All of this is sort of hand-chosen to be able to drop directly into Datomic as a single transaction. So when we're done generating actions for an agent, we do one transaction that creates the agent and its list of actions in the database. This is the loop for generating an agent. There are a couple of interesting things in here. Right there, we have model parameters creeping in. So we're still in the generator. We're still allowed to be random. We've got a model parameter for the device ID distribution. This is essentially picking random device IDs, but occasionally overlapping. So it's not fully random. And then we've got this identify early percentage. We use those random bits down here where we say for a particular agent, we're picking 3 device IDs out of the distribution. We're generating a random email address. So email address is a function that generates proper email addresses, but ones that are sometimes hard to deal with, plus addresses and extra characters, that sort of thing. And then we've got another roll of the dice here about whether you identify yourself on your first interaction, simply calling the randomness. And then we're doing it repeatedly, however many times the visitor count says we're supposed to create for this test, we just loop over that. So as I mentioned, this is creating one population that's all relatively homogeneous, but has some randomness baked into it. The next part is the simulation runner, the execution for it. So it needs to do a few things. It needs to set up the target system, because we're right about to run a bunch of actions against it. We need to execute the actions, capture the outputs, and capture internal state where it's relevant to validation. Fortunately, the runner is not as complicated as some of the other things. It basically just looks like this. We start a bunch of processes, mainly by setting a flag in the database that says go, and then we wait for them all to complete. The processes are all, or the actual runners are all sitting and waiting for that flag to turn to go. And so as soon as it does, they begin executing. When they're done, they set the flag so that this wait for completion can complete. And so we can actually run pretty much with the same code, either in a local or a distributed setup. We take care of the setup and lifecycle stuff just here. This is the start processes and wait for completion that we just saw. We retrieve some reports afterwards that's collecting the internal state from the target system. And then the rest is, well, you can see target system setup. That's probably pretty clear. The actions are each as granular as possible. And so when we want to execute one action, we want to try and keep it isolated from everything else. This is a place where this style of test differs from, say, integrated functional tests or scripted tests. So I've seen suites of tests for commerce systems, for example, where 2/3 of the tests began with the same login sequence. Well, that login sequence, because it's shared across all the tests, whenever that changes on the target system, I now have a cost associated with updating all the scripts that use that login sequence. So we want to factor these out into individual actions. Each one is repeatable, atomic, and what I find interesting is that they don't do any validation. We defer all of that for later. I'm going to apologize in advance for this next slide. I couldn't fit it on here without making the font smaller, so it's just going to look really full. That's one action. Almost all of it is sort of finding where it is in the grand scheme of things. The really essential part is right here, where we're actually calling and talking to the target system. And then right here, we're recording what we got back from the target system. The rest of it up there, it's just navigating entities in the database to sort of find out who am I, what am I supposed to present. There is two other interesting parts here, just two. You remember before we had this agent identify early flag that we were setting randomly. Well, here we're saying if it's true, then provide the email address on the request. So this is where we're using our non-determinism from the generator. But of course, every time I run through this, I'm using the same agents, and so I'm going to get the same value of identify early. So this is repeatable because I did the random stuff before. On device ID, that call to nth mod is also a trick for containing the randomness up front. So nth mod takes any collection of stuff plus a randomly chosen index, cycles the collection and finds that index in the cycled collection. Basically, a way of saying, I'm going to generate a random number between 1 and 100. I don't know how many items I'm going to get back in my collection, but if I say I'm taking the 13th item and I get the same collection every time, then I'm always picking the same item. I'm belaboring that point a little bit because it sounds great to say we're containing the non-determinism up front, but actually doing it requires sort of a library of tricks like this to apply. Okay, the very last thing we see here is the record call, and that's building our test record. So we're building a record of all the actions that we run, their timing, their results, and so on. And that looks a little bit like this. This is very specific to Simulant. The get sim services gives you back a function that acts like the recorder for you. And this is a way of just injecting a service into each of the runners. We do write all of these to local disk and then load them into the database later. And that's purely to make sure we don't interfere with the timing of the simulation by doing time-consuming database calls purely to run the simulation. And then finally, we get to the interesting part, which is the validations. So we're trying to verify these properties, both specific about individual cases and general, the global properties. And one of the things that took me a while to grok about this is that validations are really queries. Because we've captured all of the output, we've stored it all, everything has already happened. It's in the past. And so I don't need to run a lot of imperative code or write a lot of custom functions. I can just write queries against my record of what already happened. One of them looks like this. Again, there's kind of a lot on here, so I'm just going to pull out the interesting part, which is coming from that query in the upper right. This is a data log query against my simulation record. I have several inputs. The database is an input. The ID of the simulation is an input. What attribute I'm looking at and the expected value. Those are all the inputs. And then I get back a collection of tuples of the log and actual value up at the top. Now, if you're Datomic users in the house, please don't do this part where the attribute is a parameter. I've been told that's terrible for performance. Actually, I think the exact words is, it's a performance disaster. So please don't do that. But it worked in this case. And what we're trying to do is say, I'm looking at all the action logs for an attribute that doesn't match its expected value. And the way we're using that here is in a validation that says all API calls HTTP OK. So we're asking to validate all of them. The attribute we're looking at is the response code. The expected value is 200. The loop up top is going to walk through all the tuples of log and actual for response code. And then when not equal expected actual, return this data structure. Our validation failure is just a data structure so that we can decide later whether we want to print it to a console, store it in a database, visualize it in a graph, or whatever. If you were to abort the validation, then you wouldn't learn anything from the following validations. If you were to print it to the console here, then you'd lose the ability to embed this in other output styles. So just return a data structure. And finally, we have the test reports. It's going to look like some kind of a summary for consumers. Maybe you as the programmer are the consumer. Maybe you have other stakeholders who are interested. Can get visualization in here. It can look very interesting to watch. How are our validation, what's our validation pass rate looking like over time? Okay, so just a brief reminder, these were the different parts we're looking at. And in terms of the overall approach, I definitely find coverage to be a great advantage here. In a project I did early this year, there was a group of 4 QA people full-time. The first time we ran our simulation test against the target system, we found bugs that they hadn't. And that's not to diss QA people, but it is to say we were able to explore more of the state space than they were by doing a bunch of crazy stuff that was allowed by the contract but nonsensical to humans. And we can do those global validations. If you start getting into this, there are a few considerations that you want to look at. How sophisticated of a model do you need to make? The simpler models are very quick and easy to build. So you could build that Markov model that I showed you in half an hour. Very easy. The more realistic you need your traffic to be, or your activity, the more time you're going to spend in modeling. But you only want to go as far as you need to go. So you can get a lot done with traffic that is only slightly realistic. There are a lot of tricks to containing the randomness. Repeatability is sometimes challenging. So we try and make the tests as repeatable as possible. But we are testing functionality here, not hardware failures, network failures, bizarre router behavior, packets in time warps, and that sort of thing. I'm very interested in combining this approach with those approaches, but it's work that we haven't done yet. And then as far as running the test, you do want to decide how long to run this test for. If you run it for a minute, you're probably not getting very interesting results. If you run it for 4 hours, well, your results may be interesting, but you're not there to see them. So there's a balance that you have to strike, and you may think about running very short simulations before you commit code and running the full-scale simulations offline or on a CI box. We do have a clock multiplier, so you can turn up the intensity of your test. And this can be useful for load testing and making sure you're ready for traffic rushes. But there is a catch you can run into. You can turn up the frequency that you're sending actions, but you can't necessarily make the actions happen any faster on the other end. So if you turn up your clock too much, you're going to be piling up actions that aren't executing when they're supposed to because the target system just has to finish its job. So there's another balance to be struck there. So I mentioned Simulant before. I showed you some of the code. It does come some assembly required. So it provides a few things, mainly around sort of dispatching multi-methods to help you create scripts. But there are things that you have to provide as well. You know, the model, the actions, validations, a GUI, that sort of thing. So wrapping up, and maybe we'll have time for questions. There is a little more upfront investment required for doing this than something like scripted functional testing. But I will say I've seen a lot of functional test suites get abandoned because the cost of maintenance is high. And that's a place where simulation testing wins. The cost of maintenance is much lower because each thing is separated and targeted. You can change the model independently of the actions, independently of the validations. And we're searching and querying to find errors. So that's it. I encourage you to try out the framework, send me feedback. Very interested in hearing where people want it to go. Thank you. It looks like we have 2 minutes for questions. Yes?
You said that testing trajectory space is even, recovering trajectory space is even better than covering state space. What are the techniques that allow you to do trajectories rather than states?
So the question was, when I said testing trajectories through state space are better than just testing state space, what are the techniques for doing that? Well, the main technique is varying your pathway of inputs. So typically when someone writes a functional test script, the script sort of follows the same actions time after time, which means it's wearing a rut in one pathway through state space. Maybe it has some variability in terms of, you know, a position where you can randomly select from a set of user IDs or a set of catalog items or a set of account IDs or whatever. But that's a small amount of variation on that one well-worn pathway. It won't typically do trajectories like suddenly resubmit a transaction from 4 steps backward. It won't loop around the same sequence of events 6 or 8 or 10 times. But randomly generated trajectories can do that. And so just getting that randomness in sort of the decision process about where to go next, it helps emulate some of the weird randomness that humans actually generate for our systems. Okay, let's see. here on the aisle, please.
Question. Since you have an entire database of reactions, do you actually consider using temporal queries to check on temporal validation?
I have thought about it. There is a category of temporal logic that I'm looking into that says, lets you make assertions like there is no universe in which it is the case that this occurs. One area where we could do a lot more work is around bringing those validations up to higher level expressions. Right now, the validations are pretty raw queries against the database. And so it's not yet possible to even express simple temporal logic very elegantly. That would be something to add on. Yeah.
Within reach, from what I can tell.
I believe it is.
Second question, have you thought of permanent testing? You could decouple the validators from the simulation testing framework and run them while the system is up all the time.
So for the recording, the statement was you could decouple the validators from the test framework and run them all the time. I'll amend that and say if you were also sampling the same kind of outputs as you would do during the test. And the answer is yes, absolutely. You certainly could do that. In fact, during the development of Datomic, there was a sample store that was built with people making items available for sale and purchasing them constantly. And we were actually running a validator on that all the time at several levels. There was one that was actually just checking the integrity of the database, walking through the whole thing time after time. As soon as it got to the end, it would start over again. And that worked quite well. Okay, just one more. Yes?
Do you have shrinking?
Do we have shrinking? We do not have shrinking. That was an easy one. All right, thank you.